All right, well, good morning, everybody. So I'm just copying over a few things to the Pi, and let's see, what else do I need? I think that's it. SanDisk. Okay, now I can put this on the Pi. We can get this show on the road. Okay. All right, well, let's get to it then, shall we? Huh? YouTube. So we have a math and CS department channel, and not just my stuff is getting posted there. But I did set up playlists, and I'm usually good about making sure that the right videos get in the right playlist, but not always. So, yeah. All right, so let's get to it. Let's talk fun with floats. It's like Big Bang Theory, Sheldon's fun with flags. Yeah, only with floats. Oh, and I should probably get Twitch moderator on here so that I can see everybody that's online. And let's see who we got. Jack, good morning. Monsieur Lillis. Um, so, all right. Well, so last time we were talking floating point stuff, and in particular, we were talking this algorithm, okay, which was the evil floating point square root inverse square root trick. Uh, so I posted um, four papers, and I've been getting a few more on why this works, and sort of the math behind it. Um, and it's still even kind of lost in the mist of time who exactly came up with this in the first place. Carmack, who wrote this source code, says that it wasn't him. He found out about it from somebody, and so you go back the chain, and nobody's quite sure. Um, anyway, so essentially, the reason that this is working is, um, if you think about how a floating point number is stored, right, in terms of sign bit, exponent, mantissa, um, the if we want to compute 1 over the square root of a number, what we're effectively doing is trying to compute x to the minus a half. Well, what about if we took the logarithm of that? Well, then we would be computing minus a half log x, right? Um, and the uh, the way that floating point numbers are stored kind of means that we can do the logarithm relatively easily. And subtracting, well, minus a half, okay, that makes sense. But how do you have a number, an integer? You bit shift it one pace to the right. And then if it's minus, then you're subtracting. Well, look what we got right here, right? So that's kind of what's going on here is sort of a logarithmy kind of stuff, okay? We could spend probably 2 weeks going through why this actually works. And nothing would please me more than to do that, but we got other things to do. We got fish to fry, okay? All right, so what I wanted to do is go through, I mean, we saw last time that this basically works, right? I mean, does produce a pretty dang good estimate. Um, and then, but what it's doing, right, is only producing an estimate. The real work is this line right here, which is those of you who are in like numerical analysis or something, or how many of you guys saw Newton's method in calculus? You wouldn't have, Evan. It's something that if it's covered, it's not usually covered in until Math 112, not 111. I mean, you could do it in 111, but there's too many other things that you need to do in 111 to make room for it. So, all right, so what does Newton's method do? Basically, it's an iterative procedure. You give it the exact form of what you compute. So, for example, here, the fact that it's y times 3 halves minus, right, this thing right there, that is specific to the type of problem we're doing, right? Namely that we want to do 1 over the square root. So the exact look of that equation is going to depend on what specific problem you're doing. But basically what Newton's method is doing is using the derivative of a function, or in this case it'd be 1 over the square root of x, in order to, you give it an estimate and it produces a better estimate. Right? So it improves an estimate that you already give it. And if you run this a whole bunch of times, then under most circumstances, the estimate will converge to the true value, right? So if you want it to be within some ridiculous degree of precision, you just have to repeat the procedure a few, 8, 10 times. In the game, the Quake 3 source only did it once. Okay, he's got that bottom line commented out would be to do it again. Okay, but he found that for the purposes of the game, it was sufficient to just do it once for the application that was using this algorithm, which was, of course, to compute normal vectors and stuff for 3D things, right? But it was good enough, and so he just left it at that, and then therefore saved however many machine cycles it would take to do this computation. It'd take a couple, right? Okay, so what I wanted to do is sort of talk about how you would actually implement this algorithm on ARM. Okay, and the 3 steps that we really need to concentrate on are these 3, right? So the typecasting, the the floating point as an integer, then doing this evil bit shifting, and then typecasting it back to a float. Okay, so those are sort of the 3 steps that we want to go through. Okay, so the first step in C was that. So it took a floating point number y and it turned it into an integer. Okay. Now, just to make clear, in the original source code, of course, okay, this game was released in 1999, which means Carmack was probably programming this stuff anywhere sometime between 1997 and 1999. Okay. Because let's see, Quake 2 came out in I think it was fall of 97. Yeah, and so I just remember these things because fall of 99 was my first year of college, and fall of 97 was my first year of high school, and so like I kind of remember things based on dates like that. So anyway, um, okay, so the reason I mention that is that at that point, right, there were no 64-bit processors that in the consumer market, and so a long int was actually a 32-bit thing, not a 64-bit thing. Okay, um, so yeah, okay, so the Pentium, I mean, this was written for PCs, right? So Pentium architecture at the time, you had if you go way back to sort of archaic x86, it was all like 8 or 16-bit registers, and so there's some cruft left over. But anyway, okay, so we take in a 32-bit floating point number, and then this step is going to magically say, all right, take its bit pattern and just pretend it's an integer. Okay, so what's the assembly instruction that will do that? Fmove. Okay, we have a single precision floating point number, which means it's sitting in an S register of some sort. It might not be S0, but you get the idea, right? And I'm just going to copy that bit pattern wholesale into a W register. I'm not doing any data conversion. I'm not rounding. I'm not doing anything. I'm just literally taking the bit pattern and shoving it into a W register. Okay, does that make sense? Okay, so that step's pretty easy. And then at the end, we'll have to do basically this process in reverse to get it back into the floating point register. But that's it, okay? So the fun part, right, then would therefore be, are we good on this step, by the way? Right? All right. The fun part would be this part, right? Which, of course, in C is a single instruction, but for us, it's going to take um, 4 roughly, okay? So we've got to do several things. We need to get the magic number into a register, okay? We need to bit shift, and we need to subtract, okay? So how do I get this thing into a register? And this, by the way, will hopefully answer the question of what was going on with the F move when we were trying to load an immediate last time. So let's think, actually, let's go back to that for a moment. So F move, right? How wide is every instruction on this particular architecture? Every single machine instruction is 32 bits, okay? Um, if I want to F move an immediate, how many bits does it take to encode a 32 or 64-bit floating point number? Well, 32 or 64 bits, okay? So the problem with fmove with immediates is if I've got to put an instruction and a 32-bit floating point number into an instruction that can only be 32 bits, there ain't room for it, right? So we actually ran into this when we were doing just regular move of immediates in the integer land. Like if I wanted to load the immediate 1, we could do that, or 2 or 10 or some small number, right? But what about if I wanted to load in like 10 trillion, say? I couldn't do it because how many bits does it take to encode 10 trillion as an integer? More than the number of bits that's allocated for the immediate field in the actual opcode for move. Okay, so this we saw this when we were doing like the looking at move in, move k, and move z, that stuff. Yeah, okay. So solution, just define it as a constant, load a pointer, and then load it from memory. Okay, so that's what I'll do is I'll just make a constant. In this case, I'll call it magic 32 because it's the 32-bit version. Uh, I'll move the pointer to it into x1, and then I'll load the load whatever's at that memory address into a W register. Okay, so that takes 2 steps, right? Get the pointer and then get um, then actually load it in. Okay, so that's going to be what we'll do basically for loading any 32 or 64-bit float is just pull it in. Okay, now in this case, actually, this is a regular move, not an F move, because I'm loading this number in as an integer, not as a float, right? Because I want to do the subtraction as integers. Yeah? Okay, so this loads in the magic number, these 2 instructions. And then I need to take W0 in this case had the result of the previous step on the previous slide where we typecast it. Okay, I need to logically shift it to the right 1 position. And that's easy, it's just the LSR W0, W0, 1. I'm going to shift it, and that should be W right there. Let me fix those typos. This should be W, and that should be W. Okay, then I need to subtract the bit shift from the magic number, and that's sitting in W0. okay, at the end of that instruction. Okay, so does that make sense? So magic number got to get loaded somewhere. Thingies, typecast numbers got to get bit shifted. We got to subtract, and then we'll move on to the next step. Okay, question, preguntas, fragen? Nine? Okay. Looks like everybody's good on Discord, I mean Twitch. So, yeah. Okay, good. So, that's the meat of the work. Next step is pull it back to float land. Okay, and to do that, all we've got to do is, oops, here, right? So in C, right, the instruction was to take the int and pull it back into float land. And that basically just means we're going to do the reverse of what we did at the beginning. We're going to take a bit pattern from a W register and copy it wholesale to the S register, right? So that it's now sitting in a floating point register and can be interpreted as a float. Okay. Step 4, which I skipped here, was the Newton iteration, but that's just math, so that's nothing special. And then let's print it. Okay. So how do we print it? Well, printf is a princess, right? And so what kind of floats does printf want to print? It wants to print doubles, not singles. Fine, whatever. And so how do we take something that's a single and make it a double? You just floating point convert it, and that just produces the double that has the same value. Okay, so and then load the format string and print. Okay, and as usual, if I want to print lots of things, like a string, a number, an integer, also a float, right? What's the convention? Well, the first float that you want to print has to be sitting where? In register. Okay, let's back up. If I want to print an int, where does that int need to go? X1, because what's going in X0? The address of the format string. If I want to print a float, where does the float go? It's got to be in a D register because it's a float, but it's got to be in D0, not D1. Okay, why not? Well, because what's going in X0 is the address. Nothing's going in D0, right? D's and X's are separate things, okay? So the first float you want to print goes in D0, not D1, right? Because we don't need to put addresses in a D register, they go in X registers because they're integers. Okay, does that make sense? Yeah? Okay, good. All right, so yeah, having to convert it up to a double is mildly annoying, but you guys aren't going to have to worry about that for the 2 assignments that have to do with floats because those assignments I said to do 64-bit, and so everything's already a 64-bit, and you don't have to convert. But yeah, okay. All right, Gucci? Yeah? All right, so let's actually code this stuff up, right? And make sure it actually works. So let's go to Genie, and let me make a new project. And I'm going to call this in square root. And yes. And then I'm going to make a file. Okay. So how would you convert from a 64-bit into a 64-bit int into a 32-bit int? There is a I forget the exact command to do it, Will, but danger, Will Robinson, because if you go from 64-bit to 32-bit, what might you be doing? You might be chopping off 32 bits worth of data, right? So that might be a bad thing. But there is an operation to do it. Essentially, what you would just be doing is truncating the last 32 bits off. But so that's why I say danger Will Robinson. And then going from 64-bit to 32-bit float is also possible, but that's exceedingly fraught with danger because you really, really might lose some precision in doing so. So be careful. Okay. Okay, sorry, I'm just getting my desktop set up here so I can see my own code. Okay, so the first thing I need to do is, let me close this project and open the inverse square root project, and then open the file. Okay, so I'm going to make a couple of strings here. And then we'll put our main routine right in. And the strings, well, I need a format string in order to do the square root trick, right? So, or to print anything. So I'm going to do let me just say it this way. Okay, I'll just say this, right? Okay, nothing special. And then I'm going to hard code the number that we want to deal with here. So for sake of demonstration, I'll just do the number 2 because we know exactly what this 1 over the square root of 2 is. It's the 0.707, right, blah, blah, blah from trig. So what I'll do is I'll make magic 32 is the word 5F37 59DF. Okay, so that's Carmack's constant. That's actually not the optimum constant, but it's the one he used, so we'll just stick with it for demonstration's sake. And I also need the number 2 as a 32-bit float, which just so happens to be that. Okay, which is kind of convenient. But if you don't believe me, just pop open float toy and or whatever and convert it. Okay, so we're going to do 1 over the square root of 2 as our procedure here. Okay. All right. So what do I need to do? Well, the first thing I need to do is I need to get what was our procedure, right? I need to load in the number test num into a an S register. Okay. Well, actually, what's the very first thing I need to do? Um, need to expand my stack, and then at the end I need to shrink it and get the link and frame pointers back to the OS. Damn it. Okay. Right, so those are the usual instructions, right? In this case, it's not actually going to matter because we're not going to use the stack at all in this demo program. But nor are we going to be, oh, no, I take that back. We will be branching because we're going to have to use printf. So yeah, we do need to do this. Okay. Basically, if your program does no branching, you don't have to do this store pair load pair. It's only because you're branching that we have to preserve that information. Okay. So first thing I need to do is I need to move the number 2 into a floating point register. Okay. Which means I need to move oh, sorry, it should be load. I need to load X0 with the address of the test number. Then I need to load the register S0 with the thing that's found, sorry, that should be X0, that, right? So load register with the pointer, so that goes into an X register, and then I'm going to load S0 with the contents found at memory address X0, 32 bits worth, right? Okay, so we're good with that part? All right, so after this operation, what's in S0? Has that, right? It's 2 as a float. Okay. Now what? No, not yet. Typecast it back to an int. Okay. Now, in this case, I could have just loaded it straight in as an int. Okay, but in the context of the game, right, the function that was doing this was accepting a float from somewhere else. So let's just pretend that we don't want to do that. Okay, so I need to typecast. And how do I typecast? I'm going to F move S0 to W0. Okay? All right, so typecast to int. And I'm going to put spaces here for the 3 steps so that it's pretty clear what we've got where. Okay, what's next? Okay, we need to load in the magic number, we need to do the bit shifting, and we need to subtract. So let's get the magic number in. All right, so I need to load a register. Which one? Well, how about X1? Because if I put it in X0, what's going to happen? I'm going to nuke the typecast number because X0 and W0 are the same thing, right? Same physical register. Okay, so I'll put the pointer in X1, and I want, in this case, the magic 32. And then I need to load X2, well, W2 with the address found in X1. Okay? So it loads in our magic number. Okay. I also need to bit shift. So I need to bit shift W0 one position to the right. Okay, so what operation do I need to do there? Logical shift right, W0, W0, immediate 1. Yes. Yeah, it should have been LDR. Yeah. Because you're loading the pointer, you're not moving the pointer, and that's just the pickiness of it. Yeah. So no, the PowerPoint, it should say LDR there, right? If we had put move there and tried to assemble it, it would have been like, eh, and then I would have been like, oh duh, it's LDR, not move there, and right. Okay. Okay. Good. So that does the bit shifting, and then last we need to do subtraction. So we need to subtract W2 minus W0, and then let's put the answer in W0. Right? So we need to do magic number minus bit shifted value. Okay, so where's the bit shifted value after this step? So let me put in some comments here. Right, that's equivalent to the bit shift operator from C. Okay, and then we need to do the subtraction. Okay, so this is doing that. Okay, Gucci? No? Okay, so we typecast to an int. We do some evil floating point stuff. we say WTF. Then what? Typecast it back, okay? So what do I need to do here? I need to take W0 and move him back to an S register. So that would be F move, S0, W0, right? It's going the opposite direction of the first thing. So this is typecast back to a 32-bit float. Good? Okay. So that does the computation. I'm going to skip the Newton's method part that would come next because that's just math. So all we're going to do is just take whatever's spit out by this estimate and call it good from there. Okay, good. All right, so now we just need to print it. So how do I print it? Well, I need to load X0 with the format string, which, what did I call that? Out string 1. Okay, and in my string, what am I going to print here? I want to, oh, actually, I've been messy here. You know what I'm going to do? I'm going to put this in this S move right there. I'm going to put it in S1 instead of S0. Why? Yeah, because what's sitting in S0? The original number, and I don't want to destroy that. Now, you're right, I still have to do some conversion, okay? But I want to be able to print both the original number and the estimate, okay? So I don't want to overwrite S0 yet, okay? So I also need to convert, yes. Okay, so I've got to convert the two numbers to 64-bit floats because printf just wants them that way. That's mildly annoying, but sorry. Okay, and are we ready to print? We've got our format string. We've got our two numbers where they need to be. We ready to branch and link? Yep, okay. Let's branch and link to printf, and that should be it for now. Okay, so let's save it, let's assemble it, let's run it, and hopefully it works. Hopefully I didn't screw anything up. Oops. Yep, there we go. Okay, so the Carmack inverse square root estimate of 2 is 0.716, blah, 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 which is pretty close to the true value of 0.707, blah, blah, blah. Okay. So two things here. It seems to me, it seems that printf is printing only 6 decimal, well, 7 if you count what's before the decimal digits. There's probably a way that we could tell it to print more. The other thing I could do is print this stuff in hex, and then we could write down the whole hex number. Now, in this case, we already know what the whole hex number is because it'd be, what's our magic constant? What was our magic constant? 5F3759DF. Well, let's think about this. If I take 40000 and shift it one position to the right, what's it going to become? 2000000. And if I subtract that from 5F37 blah, 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 what am I going to get? 3F3759DF, right? So that's the actual number that we got in hex. Yeah. Okay. Make sense? Yeah. Okay. That's pretty cool, huh? Now, back to the old PowerPoint, because it turns out oh, I'm like, where the heck did my slides go? They got super minimized. Oops, sorry, I didn't want to talk about that. Okay, so we just programmed it, right? It worked, everything's happy, we're all good, Gucci. It turns out that there's a built-in function to do this, sort of. So the ARM64 floating point stuff has two instructions called FRSQRTE and FRSQRTS. Okay, the E for estimate and the S for step. So the SQRTE, the estimate one, produces an estimate of the inverse square root. And then the S operation, the step operation, does exactly the Newton's method thing with the 3/2 and whatnot. Okay, so and it builds it into a single operation, which is kind of cool. Now, the question is FRSQRTE, how does it work? I don't know yet. Okay, so I wrote to ARM Education and said, hey, how does this function work? I don't want to have to sit down and reverse engineer it. I mean, I could, but I don't want to because it's work. You put it on a blog? No, I just wrote an email to the ARM company. Yes. Okay. They answered you back? Not yet. They probably won't. And if they do, they'll probably be like, "Thank you for your inquiry. This information is proprietary." Blah blah blah. Right? Or to contact sales, press 1. Right? I don't want sales. Yeah. Your call is very important to us. Yeah. Primo dos. Exactly. Yeah. Well, let's just say I learned some new Spanish last night from Email War Part 2. You can see that? It got forwarded to me. Of course it gets forwarded. It probably got forwarded to like, he has a small army. Mm-hmm. I was trying to forward it, but I was saying I didn't forward it. All right. Yeah, so learn some new Spanish. It's either freshmen or it's juniors. Because I feel like my class is, sorry, Porter, my class is just very, I don't know, ignorant. No, I barely saw you guys in that change. It was literally mostly freshmen. Yeah, I appreciate you not. I was sitting there, I was not trying to pull the, like, oh, I'm better at staff, I've been here. But we don't, like, the past 3 years when we have emo chains, nobody handles it that immaturely. Yeah. In the class of 2024. I mean, I'm not gonna lie, the memes, they're funny. They're good. Not really. I mean, I got but regardless, like, it shouldn't be wired in their brains. Like, as soon as they have an email chain, like, let's harass the shit out of whoever sent the email. I mean, I like that it's a hot dog. A sandwich? Yeah, that's innocent. I was just like, that's why they don't understand the classic email chain. Right. Okay. So. We need to start the classic email chain. One that's funny. Mm-hmm. Yeah. So, all right. Well, back to floating point. Right. So it's not clear how. I was like, how did we get to that? No, because I mentioned email and And then the Spanish joke came up, and then I was like, oh, by the way, I learned some new Spanish slang last night. Um, so yeah, I had to look one of those words up. I won't say it, but starts with a J. Yeah. Uh-huh. No, I Googled. I definitely Googled so that I could get the slang. Yeah. So anyway. All right. So the E will do an estimate, and I'm not entirely sure how it's working. In particular, it is not doing a magic constant subtraction. So I tried it on a couple of different numbers and compared that to the magic number subtraction method, and I didn't get the same things. In fact, in every test, it actually beat the magic number method. Um, like it was more accurate. Yeah, the estimate version. Its its estimate was better than the magic number subtraction estimate. Now keep in mind those are both estimates, not perfect, right? So, but yeah, it was more accurate than the magic number method. No, they don't operate the same way, huh? So the yeah, whatever arm, however arm made FRSQRTE work is not the same as the Carmack magic number subtraction trick. Oh, yes. So why? Because we didn't have this in 1997, damn it. Yeah, well, okay. So we have this thing now. It's cool. Um, but, you know, but think of the joy that you've gotten by seeing this really clever trick, right? Estimate inverse square roots with this one weird trick. Like I can make like web ads and like have a picture of a rotting banana on it, right? And no, okay. All right. Anyway, as annoying as what? Oh yeah, mhm. Yeah. They never get me because I'm a J word. So yeah. So, uh, yes. I'm not going to say it because I'm live on the internet, but no, I don't remember. Oh. All right. So, yeah, talk about some blunders. Or I'll just scroll him and be like, so, uh, mm-hmm, mm-hmm. All right, so let's talk about SIMD. SIMD stands for single instruction, multiple data. And if you thought the last stuff was voodoo, this stuff is super voodoo. Okay. Um, yeah. So SIMD instructions, these things started to become part of consumer grade processors in the 90s. Um, with you guys have probably heard of like MMX or AVX or these different processor extensions. No? Okay, well, maybe. Um, anyway, what this stuff allows us to do is make a single instruction that does multiple computations on multiple pieces of data. But it sort of does it in kind of parallel. And this is super useful for graphics processing or multimedia stuff, audio, video encoding, things of that sort. So you can do some really cool stuff with it. And we're going to start with a simple example. Okay. So so Lilith, I'm not actually sure if the magic number thing is faster because the the inverse square root estimate that is built in is a single instruction. Now the question is how many cycles does it take to run? I don't know, right? So um, I haven't run testing to see like what the difference is in terms of execution time. So um, okay, anyway, so the S and the D registers, which we've used for floating point, are really part of Q registers for quad precision. And it is actually possible to do some quad precision computations on ARM, okay? But we want to think about these things a little bit differently. So rather than thinking of them as just being one giant register, we're going to think of them as vector registers that can be subdivided into lots of different slices. Okay, let me show you a picture because it makes it a lot easier to understand. Here's the picture. Okay, uh-huh. Socath, his eyes uncovered. Do you guys not get it? Socath, his eyes uncovered. From season 5 of The Next Generation, the episode called Darmok. It is. It's almost as specific as, you know, it's the flute that Captain Picard played on the episode of Star Trek The Next Generation, The Inner Light, first in his imagination and then in real life. And then Lois is like, Peter! He's like, what? I was in the survey. And then, show me Picard's flute. Bing! And there it is. And we're going to the bonus round. Have you guys seen that clip? Okay. Yeah, I should. Um, okay, so the V registers are 128 bits wide. And we can think of what we've been using before was the S and the D sort of segments within them, right? So the D is the lower 64 bits and the S is the lower 32 bits. We never use the H or the B's for floating point, or we haven't yet. You can do half precision floating point operations. And I guess in some graphics work or machine learning, that's like close enough for government work, and so you can fit more data into the registers because you're only doing 16-bit stuff. But anyway, we'll not use the halves or the bytes. So what I can do is I can subdivide. Oops, sorry. I can subdivide the V register into several lanes, if you will. And the ones that we're going to use are the ones that involve either S's or D's, right? So we can divide a V register into two lanes of D's, okay? And we can put two separate doubles into a single register, okay? So I could have two completely different double numbers, double precision, and put one of them here and the other one here, okay? Yeah, yeah, yeah. Yes. Do I need to? 128 registers that we can divide into a pair of doubles, a quad of singles, 8 half precision, or 16 bytes, right? Which is what the picture is trying to get at. Um, okay, so let me know when I can go back to the picture. S'il vous plaît. Ever, never. Yeah. Okay, everybody good to go back to the picture? Yes? Okay, thank you. All right, so there's the sort of schematic of it, right? And the versions of this that we'll utilize are really, I think, just like three or so of them, three or four. We're going to use VN So the N stands for which register, right? Because you can do this to all 32 of them, okay? Um, so we could take VN as a single 128-bit thing. We can take it VN.2D, meaning two doubles, or four singles, or two singles, where we're only using the lower half, okay? And then, of course, you can do all of this stuff with bytes and whatnot, but we'll just concentrate on the single and double, okay? In particular, so I think last week we talked about the Sine implementation, and we did a sort of quick and dirty Taylor expansion thing. All right, so the book gives, in the floating point chapter, a full program for doing Sine for 32 and 64-bit, okay, just using regular floating point. So it's a lot of fuse, multiply, add, okay. In the SIMD chapter, it does that again, but then uses SIMD to accelerate the same routine, okay? So those are our examples that to work with, or well, from the book you guys have. I'm going to do a different example with y'all today that's a little simpler to start. That will help. But then assignment-wise, where are you going to go with this? Okay, so what's the floating point assignment? What did I ask you guys to do for that? Have you guys looked? Uh, well, yeah, okay, you guys have the recursion on the table. All right, so let me remind myself exactly how I said it. Recursion, then your first fun with floats. All right. Well, the reason I need to look it up is because I changed my mind at one point. Right, okay, got it. So, all right, so the assignment is you're going to take in a floating point number that's 64 bits, okay? And you're going to use the built-in ARM command to do 1 over the square root of that number. You're also going to use the Carmack trick, okay? But you're going to be doing it in 64 bits. So what's the problem? The magic number that we have here is, it's not the same. We need the 64-bit version of that. And I linked to the paper that has the 64-bit version of the constant. Okay, so you just copy that down, and there you go. So essentially what you're going to do is part of it will be mimic what we did here, but for 64-bit, and then also throw in use the built-in ARM function and for sort of comparison's sake. That's your floating point assignment, okay? The SIMD assignment is a little bit more fun, okay? So the SIMD assignment is, well, all right, the book gives you an example for, let me just pull it up on Canvas. What am I doing? Let's not be stupid. Okay, so let me open this PDF up. Okay, so we talked, oops. So the book gives you how to do this approximation of sine using single or double precision, just regular float or accelerated with SIMD. Okay, so it gives you the code to do that, and it works, everything's fine. Okay, great. The So that's not what you guys are going to program because it's already in the book. Okay, what you're going to do is first step is to modify it. And rather than making a function sine of x, I'm going to make it sine of pi halves x. Okay, so I'll build the pi halves into it. What this means is that the user, if the user types in 1 as the input, that really corresponds to 90 degrees. And so if you take the number of degrees, so if the user inputs a number in degrees, you divide it by 90 and then pipe it through this function to get the sine of it, okay? Or an estimate for the sine of it. So I have to recompute all the coefficients, basically, is the problem. It's the same idea, and the polynomial is written in reverse order here because I copied this out of Mathematica, and Mathematica tends to put the leading power first rather than the constant term first or the linear term first, but whatever. Okay. Okay. So I just computed all those coefficients with Mathematica. No big deal, right? Um, and so you guys can implement that as a function. Basically, what you would do is mimic how the book did the SIMD sine. It's just your coefficients are different. Okay, but it's the same idea otherwise. Okay, great. Now, what motivated this is how did NASA compute sines on the Apollo guidance computer that took us to the moon? Well, it was even less than that, like 16-bit, roughly. Okay, which is really 15-bit, sort of. That are the AGC is a really weird machine because there was one parity bit for error checking, and so you didn't actually encode data with it. So parity is if the number, like you take your 15 bits, and if the number of ones is an odd number, you make the parity bit a 1. And if the number of ones is an even number, you make the parity bit a 0. And then when you get a piece of data, you count the number of ones, and if it doesn't match the parity bit, then you know that there's been an error in transmission, right? So it's the quickest and dirtiest method of um, yeah. We were within 30 seconds of aborting that landing. Yeah. Okay. Yeah. For fuel reasons. Um, well, haven't gotten us to the moon yet. I mean, we put a car into solar orbit, but no, the first stage, that's the expensive part, right? So, okay, silence, I cue you. Okay, so this was basically the routine that NASA used for the sine function on the Apollo guidance computer. Okay, it's only a fifth degree polynomial, which kind of shocked me, but this was 1960s, right? So I dug up the approximation here out of the source code, okay? And the first instance I've seen of this in print was from a book in 1955. So I was going way back for this because in 1955 there were maybe 10 computers in the world, like machine computers. There were thousands of human computers. Um, yeah. Okay. So I computed these coefficients myself, and this should be sine of pi halves x on that line there. I forgot that. So I computed the coefficients and got that version. Um, and I'm not entirely sure why my numbers are off from the Hastings book because I computed them the same way. Um, Basically, how many of you guys are in the numerical analysis class, right? So you guys have talked about Chebyshev polynomials, right? This is basically, I built a Chebyshev polynomial and then uh, multiplied everything out so that it would be a like regular looking polynomial and kept track of the coefficients, right? So where did this come from? Well, I built a polynomial by computing the the 5 or 6 nodes and then doing the, you know, the stuff, and then yeah, you guys know that what I'm doing. Okay, that's how I did it. And in fact, I'll give you guys my Mathematica notebook, and maybe you can see why my numbers don't match up with Hastings. So anyway, okay, so great. So basically what I'd like for us to do is to use SIMD to implement the classic Apollo algorithm. We don't really need SIMD for that because it's only, you know, degree 5, but whatever. And the Taylor approximation, which would be this thing. And then also, if I want to make an apples to apples comparison, and I want to compare a 15th order Taylor polynomial to the NASA thing, it's kind of unfair, right? Because the NASA thing is an algorithm built for a 16-bit machine, and this Taylor polynomial is a 15th degree thing built for a 64-bit machine, right? Kind of unfair. Okay, so what could I do? Well, the third thing to compute would be, let me take the idea of what produced the 5th degree, like how did NASA get that polynomial, and let me just crank it up to a 15th degree version of it. Yeah? So I did that, and I computed all the coefficients, and it was a big pain in the butt. But what I ended up with, all right, here's the coefficient table. Okay? Both in singles and doubles, although you guys are going to do this just with doubles. Okay, I went ahead and computed everything while I was at it. Okay, so the Apollo coefficients are those, and here they are as doubles and singles. The Taylor coefficients are down here at the bottom as doubles and singles. And the Chebyshev ones are basically, what I did was take what produced NASA's 5th degree polynomial and crank it up to 15. Right? Same idea, it was just more Chebyshev nodes. Okay, and I got that set of coefficients. Okay, and so what you guys are going to do is implement these 3 routines and spit out the numbers produced by all of them, and just we'll get to compare. That'll be fun, right? But using SIMD for the 15th degree things because that'll speed it up. Okay, so how the hell does SIMD work? Let's go back to, oh, and by the way, if you go on Canvas, let me go here, right? I went ahead and typed these into something you could copy and paste easily. Man, wasn't that nice? Yeah, yeah, yeah. Okay. All right. So how is SIMD going to work, right? What we're going to do, so let's look at an example. Now, not all of you have seen dot products before, but basically the dot product of 2 vectors tells you whether or not they're perpendicular in a geometric sense. So let's suppose that I have 2 vectors and I just picked easy numbers here. So I picked 1, 2, 3, 4 and 4, 3, 2, 1. The dot product of that is 30, and the way I get it is I multiply corresponding entries and then I add everything up. Okay, so the dot product would be 1 times 4 plus 2 times 3 plus 3 times 2 plus 4 times 1, and I get whatever I get. I just picked 1, 2, 3, 4 here just for sake of easy numbers. Okay, and 30 is the answer we should get. Now we're going to compute all this as floats, even though it turns out in this case to be a whole number, but we'll do everything in floats because we're doing SIMD. Okay. All right, so I want to write a program that does this using SIMD. Okay, what would be the inefficient way to do this? Right. I mean, we could do that, right? There's no need, no reason we have to use SIMD to do this. But what I'm going to show you guys is that the multiplication is a single step. A single operation will do that if I use SIMD. If I didn't use SIMD, I would need 4 multiplication operations. one for each pair. Does that make sense? No? Okay. So SIMD will do, like, we don't have to use SIMD to do this problem, but we can accelerate it quite a bit. Okay. All right. So the first thing I need to do is just figure out what the floating point representations are for 1, 2, 3, and 4. Okay. That wasn't rocket science, so I just wrote those down. Okay. Oui ou non? All right. Step 2. Oops. So I defined vec1 to be 1, 2, 3, 4, and then vec2 is the same thing, just in reverse order, right? Same idea. Okay. So I won't type that out. And then I want to load these things into registers. Okay. So the first thing I'm going to do is I'm going to put in x0 and x1, I'm going to put the pointers to these tables of numbers. Okay. And then this is where SIMD is kind of voodoo, right? I'm not going to use LDR. I'm going to use this thing called LD1, and there are LD1, 2, 3, and 4 operations. But in this case, I wanted LD1. So I wanted to load whatever's found starting at memory address X0 into, I chose to go into V16 here, just for fun. V16.4S. Okay, what does 4S mean? Well, how many numbers am I loading in? 4 single precision floating point numbers. So that's why it's .4S. Okay, so what this is going to do is take register V16, carve it up into 4 32-bit slices, and put one of the numbers in each slice. Okay, and then the next instruction would do the same thing, but it's going to put it in register 17 instead of 16, and it's the other one. So V16 is going to have 1, 2, 3, 4 in it, and the other one's going to have 4, 3, 2, 1 in it. Okay, just for demonstration. Okay, good. Okay, can I move on to the next slide? Yeah. All right, so that just loads in the data, and then we actually have to do the computations. Okay, so I need to multiply corresponding entries, and this is where SIMD is so cool, because it only takes a single instruction to do it. Okay, so what am I doing? I'm going to take register 16 and 17, each of which has been carved up into 4 pieces, and multiply the corresponding slices and put the answers into register 18 carved up into 4 slices. Okay, so that single instruction did 4 multiplications at once. It took slice 0 from both registers, multiplied them, and put that in slice 0 of the answer register. It took slice 1, put it multiplied, and put them in slice 1, and so on. Okay, so I did 4 things for the price of 1. Isn't that cool? Huh? Yeah? Without SIMD, that would have taken 4 separate FMOLs. Okay, good. Okay, then what do we have to do? Well, the dot product, I have to do all those things and then add them up. Okay, so this part's a little funky. I'm going to take V18 and V18, and I'm going to add them pairwise. Okay, so what it's going to do is it's going to take the 0th and 1st slice and add them. It's going to take the 2nd and 3rd slice and add them, and the 0th and the 1st slice answer sum will go into the 0th slice of the new register, and the 2nd and the 3rd slice will go into the 1st thing, right? So I've taken 4 numbers and kind of crunched it down to 2 by adding pairwise. And then I'm going to add pairwise again to get all 4 together, right? So what I've basically done is I've said I need to add 4 numbers. Take the first pair, take the second pair. Add the first pair, add the second pair. I now have 2 numbers. That's a pair, add them. Now I have a single number. Okay? Right. And once I have it down to a single number, where do single numbers go? They go in S or D registers. Okay? All right. And then after I add them up, just convert and spit out the answer. Sure. Mm-hmm. Yes. Okay. This was annoying because my gut would have said this should have been .2s. Okay, because I'm adding things pairwise, so I'm only producing 2 numbers, and that should go in .2s. I did that, and it yelled at me. The assembler yelled at me and said, "Nope, it needs to be 4s here." I think the reason why is because it's probably zeroing out the other two, the slots 2 and 3. Um, and but then here I'm only taking 2 things and spitting them into 1. So yes, I found that annoying, like weird and annoying also, and I'm not sure why they did it that way. But it is what it is. Okay. Okay. So uh, sadly, it's 9:15, which means we should quit. Um, so we'll start with the demo of this program next time. Um, in the meantime, before you guys all split, and the attendance is a little ragged today, although got a couple guys that are quarantined who are online. Did you guys like my passive aggressive Canvas post from yesterday? Yeah, because some of you have taken gratuitous advantage, right? And the end of the semester is quickly approaching, right? So I'm cracking the whip. Get me code. Okay. All right. See you guys later. Second.